Hello, and thank you for joining today's Roads and Bridges webcast. Our topic this afternoon is From Cracks to Strength, a comprehensive approach to concrete bridge repair, sponsored by MAPEI. I'm Ryan Curtis with Endeavor's Building and Construction Group, and before we dive into the great presentation, let me explain how you can participate in it. If you have any technical difficulties during today's session, simply type your issue into the Ask a Question box and a member of our team will assist you. You can also click on the question mark help button in the upper right-hand corner of the screen. We also welcome your questions during today's event. We will answer as many as possible during the Q&A session that will follow the main presentation, but please feel free to send in your questions at any time. Once again, to do so, simply type your question into the Ask a Question box and click on the send button. And lastly, please be aware that today's session is being recorded and will be available on the Roads and Bridges website within the next week. You'll be notified by email when the archive is available. Now, it's time to meet today's speaker. Rick Ellingson is MAPEI's business development leader for their structural strengthening product line in the United States. Rick's work experience includes 10 years of experience working for manufacturers of fiber reinforced polymer systems, structural pile jacketing systems, and corrosion mitigation technologies for concrete structures. More importantly, Rick has 4 young children that don't share their dad's passion for concrete repair. And with that, I'm going to go ahead and turn things over to you. Rick, the floor is yours.
Thank you, Ryan, and thank you everyone for attending. And initially, Ryan, it sounded like you said from crack to strength, and I was like, I'm not prepared to talk on this topic here. So anyways, yeah, thank you everyone for joining. Here's a little bit of presentation outline today. We're going to talk about just a review of some concrete properties, some common bridge problems that we see, best practices for surface prep of the concrete, surface prep of the reinforcing steel, some materials for concrete repair, and then also some materials for concrete protection and concrete strengthening. So a little bit background on MAPEI. MAPEI is one of the largest chemical construction manufacturers in the world. We are headquartered in Milan, Italy. Over the last 85 or so years, this kind of is an expansion of our company globally. We have 24 different product lines where about 6,000 products fall into those 24 lines. Here in the U.S., I represent one of those lines. I'm knowledgeable on that, but I'm going to be talking about quite a few different products today. So, and one thing about MAPEI being an Italian company, it has this Italian culture of quality. If you think of any Italian product that is manufactured, whether it's Italian cars, Italian shoes or clothes, suits, you always think quality, and that's a cultural thing, and it's the same thing with MAPEI's products. Being in the industry for a little bit here, I've never heard bad things about the quality of the products, and I tell people that we make a top shelf product at a middle shelf price. And for those that aren't that familiar with the ins and outs of what MAPEI actually makes and produces, a lot of us people have recognized our name because of our sponsorship in the sporting arena over the decades, specifically with cycling, with Tour de France. This year here in the U.S., MAPEI is the official sponsor of the Andretti racing team. So if you watch any Formula One races, keep an eye out for the blue MAPEI car. So although we are an Italian company, we manufacture our products here in the U.S. We have about 15 manufacturing facilities here in the U.S., about a handful of those also in Canada. And so on to bridges. So this is just a snapshot of kind of the condition of our bridges here right now. This is from the American Road and Transportation Builders Association. And as you can see, although there's a slight improvement over the last 5 or so years, we have a lot of work that needs to be done. We have about 617,000 bridges in this country, and the issues can range from concrete deterioration to corrosion issues to inadequate funding as well. And then this map here on the right, this is not the Electoral College. This is a map of states that shows the percentage of bridges that are in a poor or a structurally deficient range. And so those in the purple, you have about 9% or higher of their bridges are poor or structurally deficient. So a lot of work to be done. Over the last 24 years, this is a list of bridges that have collapsed. There's been about 40 or so bridges that have collapsed. Some of these from deterioration and corrosion, not all of them. If you look at the bottom one there, the Francis Scott Key Bridge, we all know what happened there. That wasn't necessarily from deterioration, but from a ship hitting it. But when these bridges are being built, and same with just buildings as well, they're built to be safe, but not too safe. And what do I mean by that is we can build things even more safer, but it becomes cost prohibitive. And so we try to have enough safety factors and everything else in there to make sure that is going to be safe for the public's use, but also going to be economical for us as taxpayers. Now, the Infrastructure Investment Act does offer some hope, but just the sheer scale of the problem that our bridges are facing is going to be tough to tackle. So we're going to need continued or sustained funding, and then also innovation with products and having different manufacturers bring new ideas to the table. So that's one of the things I'm hoping to do today, kind of give you a lot of the options that are out there as MAPEI being one of the larger manufacturers of these products. What can you do? So a little review on reinforced concrete. It's more than a hard gray rock. Concrete, it breathes, it moves. New concrete is at its largest volume when you first pour it, and over time it's just going to shrink. And then compare that to the reinforcing steel, where the reinforcing steel is at its smallest volume, and it's just going to expand over time. The high alkalinity of the concrete forms a protective passive layer on the reinforcing steel, which helps delay the onset of corrosion. But over time, the ingress of chlorides and carbon dioxide through the concrete cover takes place, and through the pores of the concrete by a process of diffusion, and then the onset of corrosion begins. And this is what when the passive baiting layer on that steel becomes destroyed. So what can go wrong with concrete? Quite a bit. You can have corrosion. This is something that our industry sees quite a bit from either de-icing salts in kind of the mountainous regions, DOTs that use that to try to keep the public safe while they're driving, or on the coastal areas from the salt-borne air, also working their way through the concrete cover. You could have carbonation, freeze-thaw, cracking. You could have alkali-silica reaction or delayed ettringite formation. Casting chlorides, we don't really see that here in the U.S. We see this a little more in third world countries where they're building something and it's by a beach with sand and ocean water there, and sometimes that gets mixed into the concrete and causes problems. You can have impact or abrasion damage. You can have installation defects. They form this and they pour it and they pull off the forms, and you see all this honeycombing and voids in the concrete. What do you do? And then you can have design errors and changes to the code as well. So for corrosion, chlorides are typically going to be the most common cause. And I mentioned, the de-icing salts and the coastal areas. And it takes a while for it to move through the cover, but once it gets to the steel, corrosion is off to the races. You have carbonation. This can be typically more seen at historical or industrial sites where you have a higher level of carbon dioxide. And then sulfates. This is typically coming from the soil in the ground. So the concrete is up against the soil, especially for footers and whatnot, and it can react with the concrete. Sometimes this can take a while, but I've also heard stories of projects where this became an issue a few years after new construction was being done. So corrosion in concrete. Initially, when we're putting our steel into concrete, it's a great marriage. The high alkalinity of the concrete reacts to the steel, and it creates a protective passive layer. That's what I have shown here in blue. But over time, chlorides and carbon dioxide, they'll seep through that cover, and they begin to attack that protective passive layer. And when they break down that layer, that spot becomes known as the anode. And this is what, if you see issues on your structure, the rust staining, the delamination, the spalling, these are taking place at the anodic regions on the steel. The anode is losing electrons. So the electrons are flowing from the anode to a cathodic spot on the steel. It could be right next to it. It could be another mat down. A lot of reinforced steel, concrete, the steel is all tied together so the electrons can flow to where they need to go. And when this happens, the steel at the anodic region begins to expand, and steel can expand, about 7 to 10 times its size, and that introduces additional tensile stresses in the concrete, and it causes it to crack, and then you have basically a path for more and more chlorides to get in. So there's some things you can do for corrosion prevention. So this is typically as you're looking at building a structure at the beginning, what can you do? You can really want to keep the concrete dry. This can be done through silanes, siloxanes, different types of waterproof membranes. You want to seal your cracks. You can use fiber reinforced polymer rebars, stainless steel bars, MMFX, epoxy coated bars. Sometimes for just being economical, engineers will put a higher quality bar on the top, like a stainless steel bar, and then a lower quality bar on the bottom mat, because they know chlorides are going to work from the top to the bottom. That's one option to get a little bit more service life out of your bridges. And then maintain drainage systems. This get overlooked, but you want to maintain these and make sure that the water is getting away from your bridge decks, your bridge pile caps and whatnot. And then if you have corrosion, there's different things you can do to look to mitigate it. You can coat the exposed bar, so remove the rust off the bar, coat it. There's galvanic anodes that can be used. There's impressed current systems on the market where you're hooking up to a live power source and you're pushing an endless amount of electrons onto the steel to keep it from losing electrons. There's even chloride extraction where they exploit the polarity of the chloride ion and try to pull it out of the concrete cover. And then there's different types of corrosion inhibitors that can get sprayed on the concrete as well, and they work their way in and interact with the steel. So for carbonation in concrete, this is where carbon dioxide penetrates the concrete and it reacts with the calcium hydroxide and produces calcium carbonate. This is going to lower the amount of chloride ions needed to promote corrosion. So typically if you have carbonation in conjunction with chlorides, that's a bad combination. It's just going to accelerate the problem. Carbonation is generally a slow process. It's seen more in historical structures or industrial sites. Carbonated concrete has a pH around 8.5. Where you compare that with new concrete, pH around 12, 12.5. One of the things you can use to see if you have carbonated concrete is it's called the phenolphthalein test. It's a dye indicator where they will paint it onto the concrete or spray it on. And if your concrete is pink, you're good. If it's clear, that shows that you have carbonated concrete, and then you can measure the depth that concrete has become carbonated. By reducing the pH, carbonation accelerates the time to depassivation of the reinforcing steel. Another problem is freeze-thaw or scaling. As water freezes, it expands about 9%. In moist concrete, this produces a pressure in the pores and capillaries that exceeds the tensile strength of the concrete. This cavity is going to dilate and rupture and can eventually result in scaling, cracking, crumbling of the concrete. I was subject to this just at my own house a few years ago. I was making some concrete pavers in my backyard for a patio, and I looked at the weather and I saw that the temperature was going to drop below 32 degrees for about 1 hour. I risked it. And then the next morning I woke up and I had all this scaling. So I knew better, but I won't do that again. Cracking. A windy day can cause rapid loss of moisture at the surface of the concrete. Cracking can come from tensile stresses in the concrete. You can have too much water in the mix. It reduces the strength. Excess water also evaporates and the shrinkage occurs. You have seismic events that lead to cracking, corrosion, obviously, lack of control joints, and then too little cover or too much cover. So one of the things that structural engineers can do, or just engineers, is adding additional cover to your structures. is going to significantly increase the life cycle and the durability of them. And that just has to do with you are increasing the path that the chlorides or carbon dioxide has to travel through the cover to reach the bar. And so that's, and some concrete members are going to just, per code, are going to require a little bit more cover than others. And the problem is it's not just let's add more cover, because if you have too much cover without reinforcing going through it, then your concrete's going to crack, and you just negated the whole reason for that cover, because now you have a crack. It's a deep, nice highway for chlorides and moisture to get deeper into your structure. Alkali-silica reaction. This occurs when alkalis from the cement react with certain types of silica minerals present in the aggregates. An expansive gel creates a pressure and cracking on the concrete. It's a slow reaction that occurs years or decades after construction. So a lot of people I've heard refer to ASR as the cancer of concrete. And there are things you can do on the front end. You try to opt for low alkali cement and non-reactive aggregates. There's different types of admixtures you can use that have some pozzolans to mitigate the alkali content in the cement. You can use different types of coatings or sealers or well. But if your structure does end up having this, it's hard to deal with. Some of the things right off the back is just try to seal your cracks. Try to get water away from your structure by maintaining those joints. Just kind of help reduce that reaction that's going to happen with ASR. Another one is delayed ettringite formation, or DEF. And this is a result of high early temperatures in the concrete, which prevents the mineral formation ettringite. And so this typically happens at precast yards if they're on a tight time schedule and they're trying to produce a lot of precast members. Sometimes those high early temperatures can cause problems. It causes, increases the risk of secondary forms of deterioration like freeze-thaw and attack. I worked with a port authority at one point. They had a bunch of precast piles that were put in their pier, and over time they learned that these piles had a DEF. And so what do? They can't shut this pier down. And so in that situation, they looked at trying to slow down the cracking process by applying a structural pile jacket to the piles. Another problem is abrasion, impact, erosion. This can occur from pressure washing, snow plows, vehicle impacts, wear patterns due to traffic, same with stormwater or acid runoff. Get installation defects from just the placement and the position of the rebar. Maybe we've all seen structures where they didn't get the rebar placed right, and it's right up against, there's like hardly any cover over it. Formwork placement and the support of it. If the formwork buckles or the concrete pours out. And then quality controls during mixing, transportation, and placement. There's lots of times where a concrete contractor who's going to be forming the concrete will ask the truck driver to add a little bit more water, because it's going to make it easier on him to form that and flatten the concrete. And so sometimes the truck drivers do it and they don't report, and so you have a specified mix, and now you basically, by adding the water, you're not getting what you thought you were. Cold joints, delamination, dusting. Another thing is design. And so design errors. A great example of this is with the ACI code for concrete columns before 1970s. And at that time, they said, hey, just put a 12-inch spacing on your ties, regardless of the column size. And they didn't have any hook details. And we learned a painful lesson through the Loma Prieta earthquake, where you had a significant loading event. The concrete cover cracked off, and the ties basically opened up, causing the longitudinal bars to buckle and fail. So the design community, they took a step back and they said, how can we do this better? And so now the spacing and the size of the ties is going to be dependent on the column size and on the longitudinal bars. But more importantly, they require this 135-degree hook, and that's to if you have a significant loading event, that concrete is going to put in compression the tails of that hook and keep it from opening up. So that was, that was a learning lesson, but there's still a lot of columns that were before the 1970s that have this issue. With the development of the interstate system in the 50s and 60s, road usage has exploded. A lot of these bridges were not built for the size vehicles and the frequency that we have them exposed to today. You think, last week was Amazon Prime. This week, there's a lot of trucks going over bridges delivering those packages. And then 40% of our nation's bridges are currently more than 50 years old. So some best practices. We're going to look quickly just at for best practices for the concrete, repairing it, the reinforcing steel on the surface prep, placement of new material, repair materials and their applications. And if you're not familiar, ACI has these great repair application procedures. They call them RAP bulletins, and they go into structural crack repair with epoxy, surface and vertical overhead repairs, installation of galvanic anodes, shotcrete application. So it's just a good reference if you're not familiar with that. So for the surface prep of the concrete, per the International Concrete Repair Institute, you want to square off your patches. And typically you're going to want to go 6 inches beyond the delaminated area. I know as an owner or someone who's footing the bill, you're looking at this and you go, man, this is going to take more repair material and it's going to require more labor. And that is true. But this over time has proven to be the best practice. So if you don't have the time or the money to do it right the first time, hopefully you have the time and the money to do it right when you need to go back and fix it. Edge conditioning. You want to avoid feather edging. There's a lot of manufacturers that their products will say you can feather edge it. It's just not a good practice. You can never truly go down to zero. Ideally, you want to condition the edges on these repairs by going down about 3/4 of an inch. That's going to provide, make sure that you're not going to have a weak spot where you would have a feather edge. And then the surface profile. ICRI has these different CSP chips, and depending on the product you're using, whether it's a construction grout or a bridge deck coating or epoxy or a ceiling, they're going to have a different type of surface profile that the product calls out. And the surface profile, it helps open up the pores, and it's going to provide a good mechanical bond for the product that you're using. Another thing is surface conditioning. Typically, you're going to want to have your concrete as a saturated surface dry. And what that does is it's going to prevent the rapid drying of that repair material. So if you think, you have a nice wet patch you're putting down and the dry concrete is going to suck a lot of moisture out of that wet patch, and it's going to weaken that bond interface. And so there's, to my knowledge, there's no specification or standard for how to reach this SSD, and it will really depend also on where in the country you are. If you're in Phoenix, close to where I'm at, in the summer, it's going to be very different trying to reach this than if you are in New York in the winter. I've heard some people say, you can spray the surface down, and then you can go back with a leaf blower and try to blow out any pockets of water that accumulate in the pores there. I've even heard of others that they'll take a piece of cardboard and put it where the people are using a leaf blower, and they'll see if any water is splashing up. And if it's minimal, then they go, okay, we reached this SSD condition. There's also bonding agents. These are going to provide a stronger adhesion. They'll help fill cracks or any little cavities. A lot of applications where you can bond old concrete to new concrete as well. So that's the surface prep of the concrete, just kind of 5 best practices, things to consider. So then on the steel, one, if you have a section loss, depending on how much, you're going to want to consult a structural engineer. And the different types of members will determine what's an acceptable section loss. The engineer is going to look at that and say, do we need to add additional reinforcing through fiber reinforced polymers, or do we want to cut the bad section of the bar off and splice a new bar in there, but that'll be a decision that they make. Another thing is you want to clean the steel. You want to get rid of the corrosion and any scale that can be on the bar. Typically abrasive, blasting, or water jetting are good methods to reach that. Then coating the steel. Typically, if you're going to be applying a patch material on the area that you've removed that was from delaminated, that patch material is going to have a nice high pH, and it will recreate a passive layer in that spot. But sometimes engineers, we would like to be a little bit more conservative, and we want to coat the steel with either an epoxy corrosion inhibitor that goes on it, the bar. There's different types of cementitious ones as well. MAPEI has ones where not only besides coating the steel, you could spray the product on, and it'll also act as a bonding agent. So you're kind of accomplishing two things at once. And then there's also the consideration of using galvanic anodes. And so corrosion is it's a loss of energy. Your steel is losing electrons. Galvanic anodes, you're basically just adding energy back into the system. The anodes are a zinc core, and they're going to give off electrons to the steel to keep the steel from losing electrons. So repair materials, some common questions. What properties does the host concrete have? Is the structure going to remain in use during the repair? If you have a bridge deck and say 3,500 psi, are you going to want a 10,000 psi patch material? Ideally, it'd be nice to try to marry up similar properties. Now, sometimes that can't be done because you're looking at how long do I have to close traffic off? A lot of DOTs, if you close it off for a long time, you're going to get the public pretty upset with you. And so sometimes you just want to have a repair material that has a higher early strength that's going to hit 3,000 psi in under an hour, so you can open up your bridge quicker. What's the min-max thickness of the repair area? That's going to also change the product formulation that you're going to look at to get the best product. And then what needs to be done after the repair? Is there any type of coating, maybe an acrylic coating? Some DOTs I've seen, they'll put a fiberglass epoxy over their patches that helps restrain the repair, keeps moisture from getting in on any potential edges on the crack that will develop on the edges of the repair. So for partial depth repairs, this is, you could have shallow cracking, delamination, or spalling. For these repairs, you're going to be exposing the first layer of your reinforcing steel. A great product for this is this Planning Top 18. We have an 18 extended set, give you a little bit more working time, and then also an 18 trial grade. This product is approved on most DOTs here in the U.S., and this has a high early strength. Like I mentioned, you're going to be over 3,000 psi in under an hour. Full depth repairs, you're going a little deeper. These are going to have to be a little bit more of a fluid type material. You're going to have a longer working time, but you're also going to have a longer cure time for those. MAPEI has a whole suite of these products. Our Planning Top 11, the pre-extended, pumpable, pourable. We have a self-consolidating one. This is nice where you don't need to have a contractor provide vibration to get rid of air pockets in your concrete. It's going to do that. It has super plasticizers mixed in with the mix to do that. Extremely flowable, this product. And then another one is this Planning Top 15. This is a form and pour. It has fumed silica in it and corrosion inhibitors. This works great in different types of marine environments for doing deeper type repairs. Now, with MAPEI, I mentioned we have so many products, and sometimes it's easy to get lost in the weeds. You go to our website and you're like, I don't know what repair grout or mortar I need to pick. This is just part of a table I use. It actually goes out farther, but this has just been a great reference that's helped me as I look at, what do I need as far as the depth? Can I add aggregate to this? What is my 1 day, 7 and 28 day compressive strength? If you would like this, at the end of this presentation, I'll have my contact information. You can just shoot me an email. If you like, I'll mail you a hard copy, or I can just send you a PDF of this as well. All right, so we talked about repair materials. Now let's get into protection. This can be with silanes, siloxanes, different corrosion inhibitors. There's healer sealers that are used on bridge decks commonly. Epoxy deck overlays. There's fiber reinforced polymer, and then different types of paint and coatings. So with a silane and a siloxane, this creates a hydrophobic layer which keeps water from penetrating the substrate. They act as a water repellent and effective chloride screen. So silanes is a smaller molecule size. It's going to have better penetration into the concrete, and it's going to be, because of that penetration, it's going to have less subject surface wear as well. The siloxanes, these are not going to penetrate as deep into the structure, and they're going to react more with the moisture in the air. They're better at water beading, and that picture shows the water beading properties that it has. They have better UV resistance as well. And so MAPEI has, some that are, we have a mixture of a silane with a siloxane. We have some that are just silane. These products are going to have a minimum visual change in the appearance of your structure. They're non-film forming, vapor permeable. You can use it on other things besides concrete. You can use it on clay, on brick, and on stone. It's not subject to surface wear and weathering. The surface wear more so with the silane, the weathering more so with the siloxane. But these are going to require reapplication, and it's not effective over cracks or voids. You need to repair the cracks and voids ideally before utilizing this product. And as far as, the reapplication and what one to use, I typically tell people if the structure or the concrete members you're trying to access are difficult or costly, it's probably better to go with a higher percent silane at the front end and just give you a little bit more time before you need to go do a reapplication. It's going to be a little bit more expensive, but once again, you're going to be saving on the continual application over the years and decades with this product. There's migrating corrosion inhibitors. This is a surface applied corrosion inhibitor designed to penetrate the concrete and protect the embedded steel reinforcement that reacts with the ions in this, react with the metal ions on the bar and helps perform like a protective film on the steel. It's designed to delay the corrosion process and reduce the overall corrosion activity that's taking place. It's not a vapor barrier. It does allow the concrete to breathe. You can spray this on. You can roll it on with a brush. And it does not require the removal of good concrete. There's protection, healer sealers. This is the low viscosity epoxy that's designed to flow and penetrate the finest cracks. These have a centipoise of around 80. You think of water at 0 and these are 80. That's very low. The cracks are sealed against further intrusion from chlorides, water, dirt, etc. It's easy to apply by a squeegee. There's a little surface preparation that needs to be done with this. And this really can just reduce the amount of frequent repairs and maintenance that is needed and provide some cost savings on your bridge decks. I know some DOTs are big fans of this. After application, you want to broadcast a fine silica sand and allow it to cure for 3 to 4 hours. Once again, you're working with an epoxy, so adding something that's going to increase the coefficient of friction is ideal. And then traffic can resume within 12 hours, depending on the temperature. Of course, if it's hotter, it's going to cure faster. Then there's epoxy overlay systems. These are engineered to provide a skid-resistant overlay on a concrete surface. These are also used in parking garages as well. Some insurance companies have provided information to different bridge owners and transportation municipalities, showing where a lot of accidents tend to happen. And so those municipalities or owners can look at applying something that, like this product, that's going to increase the coefficient of friction to help and also help increase the safety of the drivers. Excuse me. So this can be applied in various thicknesses to ensure optimal performance and protection. So one project down in Miami, Florida, we use several of these different types of products. This is a Brickle Key Bridge. You can see the pile caps here on this bridge. A lot of corrosion. We clean those off. We use this Plenty Bond 3C rebar coating on those. And then for the patch material, we use Plenty Top 15. That's the one that has the fumed silica in it, has corrosion inhibitors. That's sort of designed for these harsher environments. And then for the deck, we use this Plenty Seal traffic coat. And then you can see this gentleman casting some aggregate in here to clean quartz sand. There's different types of things you can use to help with that friction. So another type of product are fiber reinforced polymers, or they call them FRPs. And what this is it's a fiber that has a very high tensile strength. So you think of your standard construction bar sitting at around 60 KSI. The fibers have a tensile strength of about 710 KSI, so over 10 times the strength. Now, unfortunately, there's no way to utilize a dry fabric on concrete. We need something to cause it to stick. In those situations, we'll use epoxy. But when we use epoxy, it lowers the overall tensile strength. So it'll bring that 710 KSI strength down to, say, about a 210. I just use an example of kind of MAPEI's middle of the road strength fabric here. We also have glass fabrics as well. These are a little bit more economical, not going to have the same strength and also the same durability that carbon fiber has. And so these fibers, they're very small. I mean, they're like 1/25th the size of a human hair. And these are going to get saturated in an epoxy. The epoxy is going to protect those fibers. It's going to help transfer the load. Ultimately, it anchors it to the concrete, and it provides great fatigue resistance as well. So reasons to strengthen your structures. You could have an increase in the load-bearing capacity. I mentioned, some of these old bridges that were built were not built for the size trucks that we use today or for the frequency. I've talked about some of the design errors. There's also construction errors. I remember hearing a great case where 2 brand new bridges were being built on an interstate, and the contractor had finished the eastbound bridges, and he's working on the westbound bridges. And as he's doing that, the inspector comes by and he's looking at it, and he tells the contractor, he goes, "It looks like you've left half of the steel out of this bridge deck." And the contractor goes, "No," he goes, "I'm doing this the exact same way I did the last bridge." Well, turns out that the contractor and the first inspector missed it. And so now you have this major construction error with these, this new 9-span bridge that has been built that has half the steel on the deck. And so fortunately, the owner knew about utilizing fiber reinforced polymers after the fact to strengthen this new bridge so that it can be put into use in its full capacity. Also, another common reason is to replace the loss of capacity. This could be from corrosion of the steel. It could be from a cut or damage reinforcing steel. It could be from impact damage, a fire or other natural disasters that happen as well. Sometimes we need to beef up our concrete members. Seismic performance of a structure. This is where the material first got a good look at after a lot of those California earthquakes that happened in the 80s. And then some of the advantages of using this material, it's very lightweight, so you're not adding a whole lot of a dead load to your structure. This is great, especially for seismic retrofits where that would be detrimental to add a lot of weight. It has a high strength to stiffness. It's non-corrosive. That's just a miracle material in itself, where your structures are losing strength because they're corroding, and now you can put something that's significantly stronger and is not going to corrode. It has a low profile, about 1/16 of an inch. This works great. You think like a parking garage, putting it in the bottom of the joist. You don't have a lot of area to add where otherwise the roofs of the trucks are going to be scraping on those joists. Fast installation and cure times. Typically, by the time you put it up, 24 hours later, the system is working. And then also minimal heavy equipment is going to be required to put these materials up. So, MAPEI, we have fabrics, we have these plates that this gentleman is holding. We have different types of bars that we use, carbon and glass bars as well. So for engineers, this is just some typical strengthening ranges. Now, you know, the type of member, the existing reinforcing, the cover, strength of the F prime C of it, it's all going to play a factor into that. But typically for flexural, you're looking at 40 to 100% strength increase, shear, maybe 20 to about 150, and then axial 20 to 100. I will mention for applications where you're going to do, you're trying to increase the axial, you'll be doing like a confinement wrap. And that's actually some of the best applications for FRP. And that has to do with the material is being wrapped around itself. So you're not relying as much on the bond of the material, the fiber to the concrete. That's referred to as a contact critical. Whereas the flexural and shear applications, you're really relying on the bond, so it's referred to as a bond critical. So there's different things that the ACI guide 440 lays out for, you know, you need to test the concrete strength, the pull-off strength before. After you've installed it, you want to test to make sure that you're over 200 PSI, make sure that it's bonded properly. Two common design guides. The more common one used is this ACI 440. And the other one for some of the bridge community is the AASHTO one for design of FRP systems for strengthening concrete bridge elements. Now, the ACI 440, both of these are just a design guide, but this ACI 440, it's actually going to become a code in 2027 when the IBC releases their new update. And so I think that's going to cause a lot more engineers to feel more comfortable with it. Now, MAPEI, we like I mentioned, we're a large construction product manufacturer. We're not a structural engineering design firm, but we do participate quite a bit in that design process. MAPEI, we have this, we call it MAPEI Structural Design. It's a cloud-based calculation tool. Because we're an international company, we go follow a lot of these different international codes and guidelines. We're going to be releasing this here in the US in the coming months. And you just go through and you pick your code. So say ACI 440. I do not believe we're going to have the AASHTO to start off. And then you just, you know, are you looking to strengthen concrete, masonry, timber? And then you just pick is it a beam, a column, a slab? And then you go ahead and you put in the information on the project, and then it shows you the code you're using and the equations in the code, and it'll give you a report from that. One recent project that we're just working on is this I-395 in Miami. You have these bridge bent caps here. This shows this gentleman doing like a stirrup type wrap to increase the shear between where the column and that cap intersect there. Here's one in Lithuania. They wanted to stiffen it and then also increase the load-bearing capacity of this. They did not want to add any cross section to these piers. It's sort of like a historical site there. And so in that situation, they use a lot of these MAPEI's carbo plates going vertical. And then you can sort of barely see, we use this, the MAPEI carbon fiber that went around in a hoop direction to help give it a little bit more axial capacity. Here's a project. It's a generating station bridge in Jacksonville, Florida. I think they had like 64 piles and 63 caps that needed repair with some of our repair grouts and mortars. We also use the different types of carbon fiber plates, the carbon fiber wraps as well to strengthen this. Another type of protection system is coatings. Typically, a lot of people use the word paint and coatings, and they think it's the same thing. Coatings actually have a higher performance standard than a paint would. Coatings are going to help protect against moisture infiltration. They're going to help bridge cracks. But both a paint or a coating are going to provide just an aesthetic value, and also improves the dirt pickup resistance just compared to just a bare concrete. Now, this is another product. It's not a repair product or a strengthening product, but it is one that is used in the bridge community. We have this segmental-bridge adhesive epoxy. And so these get put on these bridge segments here that acts as a lubricant and a sealer. It has a long working time. We have them formulated for 4 different temperature ranges. So depending on your project site and the time of year that you're installing it, we have one that's formulated for that temperature range. These create a water resistant barrier as well. Another product is our post-tensioning grout, our Pliny Grout PT, and this is specially formulated to meet all the PTI specifications. It's easily pumpable, long working time, corrosion resistance, aggregate-free, silica fumed. So here's a project where some of that segmental bridge adhesive was used. It's kind of hard to see, but you look at that picture on the left. They've mixed the epoxy and they've kind of put this on by hand or rolled it on. They have it kind of into the shear keys, and then from there they'll go ahead and lift and put that into place and clamp it down. Something I'm not going to be able to get into is our admixtures. So MAPEI has a very good sized admixtures product division. They partner with a lot of batch plants around the country. And so if you're looking at and you want some more information, you could send me, and then I'll pass your contact information off to the appropriate person as well. And then as far as trying to figure out what products are approved with your DOT, our website has this information. If you go there, you can click on your DOT and it'll show you the products that we currently have approved. And then we also have a very long list that we're in the process of getting approved with the various DOTs. So they have different requirements, and so this takes some time and a lot of effort. So with that, I'll go ahead and open it to questions that you might have.
Awesome. Well, thank you. We really appreciate you sharing that presentation with us all today. Now, a few of you have already submitted some questions, so we're going to jump right in. And if you'd like to submit a question, simply type your question into the Ask a Question box and hit the send button. So let's jump into these questions. Can FRP be used to supplement the loss of capacity from broken PT cables?
Yeah, this is something we'll get a call. We see this a lot with buildings where, say, a plumber or an electrician, it doesn't scan the slab and it just punches through and he hits a PT cable. In those situations, you can use FRP to supplement for what was lost. Same with just conventional steel. There's other applications where they, for buildings, if they wanted to open up a wall or a floor and they're going to be severing bars, they can look at basically adding some FRP prior to making those cuts to make sure that there's no shear cracks that happen at the corners there.
Perfect. Is epoxy-coated bars effective at stopping corrosion?
That's a good question. So epoxy-coated bars, in theory, are great. In the lab, I think they're great. What it's trying to do is create a protective passive layer on that bar that you would typically get from just the high pH alkalinity of the concrete. But what happens is with contractors hauling the bars and everything else, if they get a chip in the epoxy coating or a little holiday in it, what's shown is they'll set up what's referred to as a small anode, large cathode ratio. And that ends up accelerating the corrosion at that nick. And so some bars can be actually severed. So it was very popular, epoxy coated bars with a lot of DOTs. Now there's been a handful of DOTs that have kind of backed away from that and said, you know, this is probably not the best bang for buck. Another issue that can arise is when you go with epoxy coated bars, you're sort of locked into that long term. What I mean by is if you wanted to apply different types of corrosion mitigation methods after the fact, all your bars are going to have a dielectric barrier in between them. And so you can go in and make a little nick the holidays and tie bars together to try to get electrical continuity, but it just adds to the project complexity.
Perfect. What new products is MAPEI planning on bringing to the market in the coming years?
That's a good question. So I can't really speak for all the different product lines. I know with the one that I work in, we're looking at bringing an ultra high performance concrete to the market in the coming year or so. It's something that we're using quite a bit in Europe with tremendous success. And so we're kind of analyzing the market here. If some of you are currently using UHPC on your projects, I'd really appreciate some help, some insight into that as we navigate bringing that here in the U.S. as well.
Next question is, how do you use FRP for axial repair or strengthening?
So to do an axial repair, you're typically going to be doing like a confinement type wrap around your concrete member. And so as it gets axial loaded vertically, the concrete wants to dilate and expand outward, but that FRP is going to lock it in and keep it from doing that.
Got it. Does silane seal cracks or just concrete surface?
Just the surface. So like if you have cracks, it's best practice to have those patched or addressed before putting the silane sealer on them.
Perfect. Are there any studies done to quantify the effect of the concrete distress, cracking, spalls, etc., on the overall durability and hot to account that in the design phase?
There probably is. I don't have any on the tip of my tongue that I can refer to, but I'm sure there's studies that are out there that could look into that.
Perfect. How effective are the skim coat concrete surface repair products? 1/4 inch top coat products, or specifically in question, the lamination ?
They're effective, but like with any type of product, the most important thing is the surface prep. And so that's why I spent a slide kind of going over the surface prep of the concrete, because you can have the best product in the world, but if you don't have the right surface prep, you're opening yourself up to having problems later in that area.
Got it. Did you experience a repair that you decided it is unrepairable?
They are out there. I haven't had that with MAPEI, but I have had that with other companies as I've looked at different projects where we just kind of have to back away and say, this is just, it's too risky. We don't feel comfortable with this. I'm in a little different position now, just solely representing a manufacturer, whereas before I was with manufacturers that had an engineering element and had a construction element as well. And so we kind of have a deeper dive, and we were taking on a little bit more risk. And so there were some repairs that we said, not for us.
Perfect. How are existing rusted/exposed rebars typically prepared prior to applying a coating?
You can use Wire wheels work good kind of on a smaller level. I've seen sandblasting, water jetting as well. Those are all, some options that you could consider.
Perfect. How often do you need to reapply silane, siloxane? And can you use it? Can you use it on concrete slabs as well?
That's a good question on how often that needs to be applied. I would need to look into that. I'm sure, depending on the environment and everything else is going to be a factor. I haven't seen it used on slabs. I usually see it on vertical surfaces or overhead surfaces. With the silane, I mean, it is, because of the molecule size being smaller, it is going to work deeper into the concrete. So having it wear off through abrasion from like tires or something like that is not going to be as big of a problem as it would be with like a siloxane that is not going to penetrate as deep into the structure.
Perfect. Should they be applied skinny layers or thick?
This is the silanes?
No, this is a new question. And it just says, should they be applied skinny layers or thick?
It depends on the product we're talking about.
Fair enough. What is the reapplication frequency for the silane treatment on bridge barriers?
That I'd have to look into. I think, the different percentage that you have, you can have like a 40% silane, a 60% silane, and 100% silane. Depending on the percentage that you use is going to give you a little bit longer time. Just like, last year I rolled my roof and I'm given the 7-year option, the 10-year option, or the 12-year option. And just, whatever I wanted to spend is going to determine how much longer till I'm back up on my roof and re-rolling that. Same with these silanes. I think you're probably going to be getting 10 or so years out of some of the higher silane percentage ones.
Perfect. Are any of your surface applied strengthening and or protection products NSF 61 certified for drinking water applications?
So we have NSF on other products. To my knowledge, we do not have that on our CFRP. There are some manufacturers that do that. They actually do a lot with repairing buried underground water pipes. And so that is something that they want to have that certification. Typically, the certification is going to be not so much on the fiber, but more so on the epoxy. And so one thing you could consider if you wanted to use our material on underground buried pipes and you needed that is to go over the material with something that has that NSF 61 certification.
Perfect. Any recommendations or suggestions for existing UHPC structures?
I have to get back on that one. I mean, they're great for bridge elements where you're going to be precast elements are going to be pouring it in between. I mean, you're according to the ACI 239, you need to have I think a compressive strength of 22,000 psi. That's going to be significantly higher than the other areas, and so it does act as a great bonder. It also can be used over bridge decks as well. It has a high resistivity, so it's great for corrosion. In Europe, we've also used this on columns as well, in lieu of using FRP to strengthen them, because one of the weak points of FRP is it is prone to problems with heat. So like if you're getting up above 140, 180 degrees, the resin just begins to soften. They call it the glass transition temperature. And so it's an issue like if you have a fire, FRP can be an issue, whereas UHPC, it's not going to have that issue. So in areas that are more subject or more concerned where you're going to have a fire event, UHPC is a good option in lieu of the FRP.
Perfect. Unfortunately, I think we've run out of time for today. So for those questions we didn't have time to answer, we'll be getting back to you via email. And that concludes today's webcast. On behalf of Roads and Bridges, I'd like to thank Rick for his interesting presentation, MAPEI for sponsoring today's event, and of course, all of you for joining. Have a great rest of the day.
Yeah, thank you.
Hey, thanks, Rick.
I appreciate it.